This video will introduce you to finding roots of polynomials. So what does it mean to find the roots of a polynomial? Finding the roots of a polynomial equation means finding all values of the variable that make the equation true. To find the roots of a polynomial equation of degree 2 or more, a common method is to set the equation equal to 0 and then solve. The following statements are equivalent. Find the roots of the equation ax squared plus bx plus c equals 0. Find the zeros of the function y equals ax squared plus bx plus c. So in that case, you would let y equal 0. Or find the x-intercepts of the graph of y equals ax squared plus bx plus c. Recall that to find x-intercepts, you let y equal 0. So they all really boil down to ax squared plus bx plus c equals 0 and solving that. The above equivalent statements also apply to higher degree polynomials. Notice all of these were for quadratic, but if you wanted to find the roots, zeros, or x-intercepts of higher degree polynomials, you would follow the same steps. You would set it equal to 0 and then solve. In this video, we're going to look at solving by factoring. We'll do some separate videos where we look at different methods, but this one we're going to factor. So if you are solving a quadratic or higher degree polynomial equation by factoring, what you want to do is first set the polynomial equal to 0. That's very important. Then arrange the terms in descending order by exponent. Factor the polynomial using the methods you learned in the last homework. The zero factor property tells us that if a times b equals 0, then letting factor a equal 0 will find a valid solution, and letting factor b equal 0 will find a valid solution. So let's look at this first example. We want to solve x squared plus 9x equals 0. So it's already equal to 0, so I'm good there. What I want to do is factor. So in this case, I have a greatest common factor of x. So if I just rewrite this as x times x plus 9 equals 0, then I can use this zero factor property. So I have x times x plus 9 equals 0. So x is like my factor a. So I would get x equals 0. And the x plus 9 is like my factor b. So I would get x plus 9 equals 0. Notice I still haven't solved for the x in this second equation, the x plus 9 equals 0. So I have to go ahead now and solve for x, subtract 9 from both sides, and I get x equal to -9. So I have x equals 0 and x equals -9. These are the roots of that polynomial, or the zeros, or the x-intercepts of the equation. So we could think of the roots as x equals -9 and 0. That would be my solution. Sometimes the factoring is a little more difficult, but the process is going to be the same. So let's look at example 2 here. I want to solve 4v squared plus 20v equals -25. So the first thing I notice is that my equation is not equal to 0. So I need to go ahead and set it equal to 0. So I'm going to add 25 to both sides. So I'll go ahead and rewrite this as 4v squared plus 20v plus 25 because when I'm moving this over, I have to add 25 to the right side to get the negative 25 to cancel, and add 25 to the left side of the equal sign. So I get 4v squared plus 20v plus 25 equals 0. Now, following our normal factoring methods, first I would look for a greatest common factor. 4, 20, and 25 do not share a common factor other than 1, and so I cannot factor any number out. So because I have a digit that's not equal to 1 in front of my squared term, I'm going to go ahead and use the AC method for factoring. So the AC method says that I want to multiply A times C together. So A is 4, B is 20, and C is 25. So A times C would be 4 times 25, which is 100. So I want two factors of 100 that add up to be the B coefficient. So I'm going to go ahead and think of some factors here. I could, of course, do 1 and 100. I could do 2 and 50. I could do 4 and 25. 5 times 20. I could do 10 times 10. And those are all the factors of 100. So I want a combination that multiplies to be positive 100 and adds to be positive 20. So they have to have the same sign so that they multiply to be a positive 100. And I want my result to be a positive 20 when I add them together. So the combination that would work here would be a plus 10 and a plus 10. So again, we're looking for a combination that multiplies to be AC, which was 100, and we want them to add to be B, and B was 20 in this example. All right, so in the AC method, once I get those factors, I split the BX term, split the BX term, and so I will have 4v squared plus 10v plus 10v plus 25. And I'm just factoring here, so I'm not going to put the equal 0 at this point. I'll come back up here at the end and make it an equation. So now I want to factor by grouping. So I'm going to group the first two terms and the last two terms together. So I'll have 4v squared plus 10v in one set of parentheses, a plus between my two groups, and then in my second set of parentheses, I'll have 10v plus 25. Okay, so now I look for the GCF here. So in this first group, my greatest common factor is 2v. So what number goes into both of those terms? And in my second set of parentheses, my second group, my GCF is 5. 5 goes into both 10 and into 25. So I factor out that GCF from the first group, and I have 2v times 2v plus 5. I'm going to factor the GCF from the second group, so I'll factor out a 5, and I get 2v plus 5. Now at this point, the two things in parentheses have to be the same, or else you've gone wrong somewhere in your factoring by grouping. So now the greatest common factor is 2v plus 5. And so I'm going to go ahead and factor that out as my GCF. And so my final factored form will be 2v plus 5 times 2v plus 5. Now notice this actually ended up being a perfect square trinomial. So I could have done the shortcut and said, okay, it's a perfect square trinomial, it fits the pattern, and so I could factor it quite easily by taking the square root of the first term and the square root of the last term and writing it as 2v plus 5 quantity squared. But if you don't recognize that it's a perfect square trinomial, the AC method will always work. All right, so now to solve, I'm going to go ahead and write the factored form 2v plus 5 times 2v plus 5 equals 0, or I could write it as 2v plus 5 quantity squared equals 0. And that gives me 2v plus 5 equals 0. Now the second factor is the same, so actually I don't have to solve that one in this case. If I did, I would get the exact same answer as solving 2v plus 5 equals 0, so what I'm already doing. So I get 2v equals negative 5, so v equals negative 5 halves. So this is going to be the root of that quadratic, or the 0 of the quadratic, or the x-intercept of the function 4v squared plus 20v plus 25. Now, how do we check? The way that we check is we take that number and plug it into our original. So let me pull up a calculator here. I'll go ahead and pull up the Desmos calculator. And I have negative 5 halves, and I'm trying to plug it into this original equation. So I have 4 parentheses, negative 5 over 2, close the parentheses, and square. And then plus 20v, so plus 20 parentheses times negative 5 halves. And if I've done my problem correctly, I should get a negative 25. So negative 5 halves is the correct answer, because when I plug it into the original, I get the correct answer. The two sides of the equation are equal. So I've got v equals negative 5 halves as my final answer. All right, when you're already given a factored form, what you want to do is see if you can factor any more than you already have. In this case, I have a quadratic w squared plus 9w plus 18 times a linear function, 5w minus 20. So for this one, w squared plus 9w plus 18, since there's just a 1 in front of the squared term, I can go ahead and use the fact that I need 2 factors of 18 that add up to be 9. So I'm going to go ahead and list my factors here. I have 1 and 18, 2 times 9, 3 times 6. Oh, there we go, 3 and 6. So these multiply to be C, so that those multiply to be 18, and they add to be the B term, the B coefficient. So they add to be a 9. So this is, they multiply to be C and they add to be B. Okay, so this will factor as W plus 3 times W plus 6 And then, of course, I have my 5w minus 20. I don't want to forget that one. All equal to 0. And now the zero factor property tells me that each factor, since the equation equals 0, each factor can be set equal to 0 to find all of the solutions. So I have w plus 3 equals 0, w plus 6 equals 0, and 5w minus 20 equals 0. Now notice I could have factored out the greatest common factor of 5 from this third set of parentheses, but since I'm just setting it equal to 0 and solving, it was unnecessary in this case. So w plus 3 equals 0 gives me w equals negative 3. W plus 6 equals 0 gives me w equals negative 6. And 5w minus 20 equals 0 gives me 5w equals 20. Divide both sides by 5, and I get w equals 4. So my solutions, or my roots of this equation, are going to be w equals negative 6, negative 3, and positive 4. Notice the signs on the roots end up being the opposite of what you see inside the parentheses. So w plus 3 gave us negative 3 as a root because we're setting that factor equal to 0 and then solving. All right, now let's take this concept and apply it to what we would do if we were given the roots and a leading coefficient, and we were asked to find an equation with those roots. So I'm going to use the zero factor property in reverse. So if the roots are negative 1 and 3, then I know that x would be equal to negative 1, and x would be equal to 3 would be my solutions. So if I want to use the zero factor property in reverse, that would give me x plus 1 equals 0, and that would give me x minus 3 equals 0. So basically, I used the zero factor property in reverse. So I took my solutions and I figured out what would the factor be that would have to equal 0. And so my quadratic equation would be y equals leading coefficient of 2 can be written out front. So I'm going to put the 2 out front. That's my leading coefficient. And then for the first factor, I'll put x plus 1. And for the second factor, I'll put x minus 3. That would be my solution. So that would be the quadratic equation. Remember, quadratic means degree 2, and I have an x term times an x term. I'm sorry, an x factor times an x factor. So I would end up with a degree 2 polynomial. So it's a quadratic. And notice the factors have the opposite signs of the roots. Just like up here, my roots had the opposite signs of the factors. So I'm using that zero factor property in reverse to figure out what the two factors needed to be in order to get these two roots. So quick summary, if you're trying to solve by factoring, use the factoring methods that we've learned so far. And if you have a leading coefficient it's not going to contribute to a root. It will just be a number out front. Once you factor, use the zero factor property and you can solve.